Good afternoon, everybody. Today I'm presenting you UVerse, a miniaturized platform for the implantable Internet of Things. This was a work in collaboration with Neodate, Francesco Escuccia, Emre Miros, and Tommaso Merodia. Very briefly, what I will cover. Firstly, we will look at the implantable Internet of Medical Things and why it has so much potential to revolutionize the healthcare landscape. And then we will look at how UVerse, the system that we propose, can enable the Internet of Medical Things. But first of all, what is the Internet of Medical Things? You can think of it as a system of interconnected medical devices that have some form of connectivity, and they are integrated in wide-scale networks with the ultimate goal of improving patients' life. The implantable Internet of Medical Things further extends this concept to combine futuristic implantable medical devices with the more traditional Internet of Things. And because of the Internet of Medical Things will enable new functionalities that are not available today, this is how it can improve patients' life. And specifically with the remote monitoring, you can imagine that a patient can be monitored 24/7 in situ and without the need of being in close proximity of the doctor. Furthermore, because of this, also a faster response to critical events and even life-threatening events will be possible. For example, like a heart attack or seizure in the patients who suffer from epilepsy. And of course, also new business models will be possible because systems where data, medical-grade data, medical devices, and people are all brought together still does not exist today. And the question we should ask ourselves is exactly this, is why is it possible that a system that can bring so much value and that can improve the quality of life of patients is still not out there? And the reason why is because we still don't have an implantable platform that can perform the four core functions of the implantable Internet of Things, which are sensing, computation, communication, and actuation, while at the same time also allowing end-to-end operations with a doctor or a hospital facility, which means allowing a doctor to interact directly with a board remotely. A system like this, of course, cannot run on traditional batteries because they will be depleted way too quickly. So the system needs to have needs to be rechargeable. Of course, a system like this needs to react in real time. And by real time, we mean in the order of hundreds of milliseconds or a few seconds. The system also needs to have some form of reconfigurability, both on the communication step, because we cannot have a system that does not change, especially if we think we want to have a long-term vision of the system. And it also has to be reconfigurable for the application, because having an adaptable application, medical application is a need, and especially with the futuristic devices that will be even smarter. We can have systems that can do all this and last for a long time, which means that they are very energy efficient, and of course they have to be miniaturized because we need to be implanted inside the body. Of course, some of these problems are not completely new to the research, and especially when it comes to implantable medical devices, the major issue is the powering. So, especially in recent years, we have assisted to the development of plethora of implantable medical devices. Some of them propose new powering strategies, for example, based on wireless radio frequency or electromagnetic charging, inductive coupling, and even ultrasonic waves. Other systems also have some form of connectivity already. And they are based on electromagnetic fields, radio frequency, but many of them are still passive. It's still a backscattering type of communication, so which means it's passive. And most of these devices are not reconfigurable, or for sure not in real time. The major issue with these devices is that they address only part of the problem that I described before. So, for example, now we have devices that have been aggressively miniaturized, which makes them greatly to be implanted inside the body, but because they are so tiny, now there are resources in terms of energy, computation, and communication. So, for example, there are devices that are so small, and with one single charge, they can perform one or two operations, but then they need to be charged again. Or because they don't have enough computational resources, they can perform only a few tasks. and they are not flexible enough. Other systems that are more flexible are still prototypes or still run on batteries. And all this is not without a reason, of course. And that's because we are moving a very challenging environment, which is the human body. The human body is very harsh to the communication and propagation of wireless waves, wireless communication. But it's a problem not only for the communication, but mostly for the powering, where we need to deliver much more power to the implant in order to charge it. And of course, we cannot just increase the power because we want to act in a way which is safe, and we want to realize devices that are safe for the human body. Moreover, the FDA in the US has a very strict regulation, both for the implant and for the amount of power to which we can expose the human tissues. Of course, you realize that what we're trying to do is realizing systems that with a very small amount of resources in terms of energy, communication, and computation can transfer data and power over relatively long distances affected by very high attenuation. And as if all this is not enough, we need to have devices that have to be miniaturized. Which also there's another problem, which is that of hardware use. Can we use the same hardware to perform several operations so that we can save space? Can we use off-the-shelf components, which is what we want to do with our system because we want to give a blueprint for implantable medical platforms. And so the big challenge for us that kept us busy for a little bit of time, and by little bit I mean years, is realizing a system that with very limited resources could be very efficient in the way it transfers, stores, and then manages and uses the energy to power the implant. And this is why we realized we propose UVerse. And UVerse is the first implantable Internet of Medical platform that bridges the gap in research and in technology between the doctors on the one hand and the human body on the other. And it positions very differently from state-of-the-art technology because by trading part of its size, so we have a slightly larger board for more resources. Now we have a platform that allows a doctor to monitor a patient remotely for long periods of time and allows the doctor to interact with the patient even in case of a critical event. And in our vision, this is how UVerse can enable the Internet of Medical Things. So from the bottom, UVerse has a sensing interface which means that it can collect the sensory data, process them on the board, and then use an ultrasonic interface to communicate, to transfer data with an external receiver. We also use the same ultrasonic interface to power the board. And there are many reasons why we decided to go for ultrasonic waves rather than radio frequency. First of all, because we want to have a device which is batteryless, and so we need a way to recharge it. Ultrasonic waves are attenuated much less in human tissues when compared to radio frequency. And this is a previous slide that shows basically compares the two. And which also means that the FDA allows higher exposure limits for ultrasounds rather than radio frequency. And so this is UVerse, and I'm having one in my hand. And this is this is a board that with a surface smaller than a penny can offer at once closed loop operations, communication, wireless communication based on ultrasounds, wireless ultrasonic charging, and we claim that is FDA compliant because with the power that we use to charge the board is much less than the limit of the FDA. Allows end-to-end operations, and these are reconfigurable both for communication and computation levels, as we will see later. But let's look at UVerse from a more technical point of view. This is the system architecture. UVerse is composed of three main units, which are the energy harvesting unit that basically receives and stores and manages the energy. The processing and communication unit basically allows the processing on the board and implements the transceiver interface. And then it has other interfaces to be connected with the actuators and sensors. More specifically, The energy harvesting unit features an piezoelectric transducer that receives the acoustic energy and converts it into electric energy. The matching circuit assures us that we can maximize the power that goes from the transducer to the storage. The switch is actually a novelty in Universe, and it's a fundamental component because it allows to switch between two functions, which are the harvesting and communication and processing. But at the same time, here also comes the concept I was talking about before, which is the hardware reuse. Because with the switch, we can use only one transducer, both for harvesting and communication, which basically allows us to save space, but also to reduce fabrication costs. And the rectifier receives AC signals and provides in output a constant voltage, which is what we need to charge the battery. The processing and communication unit is actually a very complex part of yours, but I would say that two core elements here are the microcontroller and the FPGA, because the combination of these two powerful elements allows the reconfigurability of the board. And the FPGA, which is featured on Universe, is actually the smallest that can be found on the market at the moment. I'm not going into the details of the architecture because we borrowed most of it from a previous work, but this is basically an ultra-wideband ultrasonic communication interface. It uses position modulation and also implements spectrum spectrum and frequency hopping. And we still had to adapt this schematic, this architecture to our needs and miniaturize it and so on. And finally, UVerse can be connected with actuators and both digital and analog sensors, as we will see in the experimental part. So the ultrasonic interface basically defines the remaining part of the system, so it's fundamental. And the first thing that we had to do with this respect was defining a mathematical model of how the power is transferred from outside of the body to the implant. And from this formulation, you can see that we can calculate the received power given the transmitted power. This is a fundamental because, firstly, this way we can design the remaining part of the system. Because this way we can also design the storage, and we know how much power we can deliver to storage and how long it's going to take to charge it. And also we can calculate the efficiency of the system, which is the crucial metric for evaluating the performance of the system. And as you can see, the formulation also has the conversion efficiency of the transducer, which is something we didn't know in the beginning, and that's why we had to realize this setup measurement to measure basically what is the power, the acoustic power that we transfer with our transducer. We only know the electric power, but not the acoustic. And this is fundamental because if we know the acoustic power that we can transfer, we can compare it with the FPGA unit. Now, bear in mind that UVerse can store even 1 million times more energy than state-of-the-art technology, which means that to be able to transfer so much energy, we need, of course, to deliver it at a very high power in the order of hundreds of milliwatts. But realizing a system that does not comply with the FDA has no commercial and no clinical future. And that's why we have to strive for a long time to try to keep this limit very low. And eventually we realized a system that basically can be powered with less than 50% of the limit of the FDA. In terms of implementation, this is the schematic. The first two are the top and bottom of the communication board. Third one is the energy harvesting board. And you can see the FPGA, the microcontroller, the clock that we use for the internal logic. And on the other side, we have the diodes for rectifying the signals and the matching network. And I hope that now this picture makes more sense for you. The two in the middle are the top and bottom of the communication unit. Up left is the energy harvesting. And these boards can be stacked one on top of each other in order to save space. As for the experimental evaluation, we use the phantoms, real porcine meat, different types of meat, homogeneous, layered. And this is a very fundamental result for us. Firstly, because you can see from here that the mathematical model follows the measurement very closely. So we are basically validating our mathematical model through measurement. But also because if you see closely, for different values of the electrical power that we transmit, we can calculate how long it's going to take to charge a certain component, whether it's a very small or a larger supercapacitor. And this is fundamental because firstly, this way we can design the system before producing it. But secondly, we can give a very accurate value to the patient. We can tell a patient how long the device needs to be charged, for how long. And these are two applications of UVerse, where we want to show basically the functionalities of the system. The first one is an end-to-end closed-loop application. And to show how UVerse can work in a more general context, we first define this task. A task is a sequence of functions that the device can perform. So we first have, in this case, a sensing for a few milliseconds and uses a certain amount of power, followed by processing of the sensory data, and then the data transmitted outside of the body. The device goes to sleep for a few hundreds of milliseconds and then enters the data receiving phase. And this is the most energy consuming one. It is important because it will have implications, as we will see soon. This is the test bed. So you see UVerse on the one side of the piece of proximity that transfers data back and forth with the receiver on the other side. The data are collected by a computer or any other mobile device, and then this way can be transferred to the cloud, to the internet. And firstly, we wanted to see what happens if we change the duty cycle, how long the device can last. By duty cycle, we mean that the UVerse firstly executes the test, then it goes to sleep. And if we change the duty cycle of this operation, how long one charge of the system can last, in the case if we power it with a battery, a rechargeable battery, or when we power it with a supercapacitor. And we noticed that with the battery can last more than 600 hours, which is about 25 days. With the supercapacitor, 40 hours, a couple of days, which is still a very good result. But using a supercapacitor is still preferable than a battery because on the long run, the supercapacitor can be charged an infinite amount of times. With this other plot, especially the one on the right, we want to show how long the device can last if we change the amount of bytes that we transfer during the transmission phase of the task. And you can notice that if we use smaller packets, the performance of the system decreases. And the reason why is because if we have smaller packets, we enter the receiving phase more often. And as I said before, that's the most energy consuming one. And finally, this is another application, more specific one actually. It's a reconfigurable pacemaker where we want to show firstly that UVerse is capable of actuation, which we haven't seen yet. And then it's reconfigurable during operation. So this is an application point of view of UVerse, but it's basically the same system. And if you look at the test bed, here we attach the UVerse to a pacemaker lead. And on the oscilloscope, you can see the pacing pulses. But most of all, you can see that the duty cycle of the pulses it changes. It's not constant, and we change it on the fly during communication, during operation of the system. So we hope that with UVerse we have given a blueprint for next generation implantable Internet of Medical Things. The very next natural step is to realize a network of UVerse boards in order to realize applications such as distributed sensing or multi-point actuation inside the body. And we already have very good promising results for artificial intelligence algorithms that can be run directly on the board for embedded systems. And the bionic sonar where I am working, we are using this technology to realize wearable, and we are pushing it really hard to realize more implantable medical devices in collaboration with the NIH, the National Institutes of Health. And if you want to know more, feel free to visit us at northeastern.edu/WAT.